Oh, cool.
I was really upset.
The no handwritten homework. Or
No, I was talking about the first one where it's like,
or 4 out of 5.
it was like, yeah, it was 4 out of 5.
Yeah.
Yeah.
I was very upset. You finished I finished the third homework too.
I haven't done the third one yet. I was just finishing typing up the second one.
Yeah, so it was pretty easy. It's like G data and 8 over. It's pretty simple.
Did you finish the video lectures of the board?
No, I haven't
Yeah, I mean,
started with it.
Wait, wasn't that the dualities? Or was that fields?
that's in the second week.
That's more aperture stuff, right?
Did you spend the apertures?
What?
Attendance are reflected for the apertures. I don't know, but. Homeworks.
Yeah, I mean, that's in all the different posts.
It's like David Fossey.
Wow. In the undergrad.
I remember everything pretty well. And
It was much simpler.
and work.
I did that data.
So. False plus matrix index. That's slash I.
What's ending?
Hmm?
What's ending? Integral.
Yeah. Yeah. So then there's some latex. So like math and yeah. I'll say like R.
What? No. I barely started.
Why did you roll on that?
Well, you have to learn it for overleaf.
Overly.
It's latex.
Okay.
Yeah, you have to learn it. You'll learn it over and over. Okay, well, thank you.
Took me you get your questions answered? Yeah. Nice. This said my gift was looking pretty good. Yeah. I hope mine looks pretty good someday.
I just finished homework.
We're getting my 7-6 completely changed my whole week. I know that just I get to spend more than one day, which is nice for my brain. And I'm already really feeling like I'm looking for so much.
What I had, I was in my real high grade source.
Digital stuff. Oh, nice.
And I had to plot the directory.
Oh, yeah, 'cause that wasn't, I mean, I'm sure it's all in the book too.
How's it
Everything
going?
concise.
Yeah.
Good.
Is that a James Madison? Oh.
Where I went.
Feel like. Yeah, what I was looking for was much simpler.
Oh, really?
It's just expanding the wave equation and substituting the x delta x squared plus delta y squared.
What was it?
Okay.
With z beta plus
5K where like Andy was wearing
with when we do z nabla squared nabla squared f plus beta z equals 0. We just distribute the
Michael, we
Washing
shared already.
over it, and then we can just substitute the parts we want with the parts on the other side.
Okay, good.
She was actually there before I was.
Very good.
I hope we got
First
extended.
problem.
All right.
I go through garage.
You already finished.
Takes forever.
This one. There's a lot of code. You have to call it every single time. You do the if you do this, you do the cross pipe or something like that. So you do it. I think the first.
Yeah.
Which is good because I've never right now.
Is this the same? This is my focus right now. Yeah, it's Cam.
Let us do and so I did type up.
Yeah, I think it's no problem.
Okay, what are we missing? Action. And let's see, 4, 6, 10. Okay, 4 o'clock. Let's go ahead and get started. All right, so just a couple of clarifications on the homework. Problem number 2 asks you to design a rectangular waveguide for a particular operating frequency and for a particular set of modes, TE10 and TE20, right? So you have to come up with what A and B should be. And since we're talking about TE0 N modes, then the B dimension doesn't contribute, right? Okay. But I sent out a clarification that we might as well pick B related to A as A equal to 2.25B. That's the dimension ratio that we've been using for the examples in the notes, and those are taken from a commercial standard waveguide of WR90, right? So A should equal to 2.25 times B, right? If you haven't started it. All right. But there's another thing. So that means you can use this formula right here. Okay, this formula here, and plug in the cutoff frequency of or to calculate the cutoff frequency of the TE20 mode, and you can calculate A from it, right? Because N is 0. So then you have everything. M is equal to 1. You have the parameters of what's inside the waveguide. You can calculate what A should be as a function of the cutoff frequency, right? Okay, but the cutoff frequency is a function of A, of course, right? All right, so what should by choosing different A's, the cutoff frequency of the 2.0 mode changes, right? But what should we choose? So what you want to do is choose, okay, so here's another observation from there. We have the observation that the attenuation constants that you calculate for the TE20 mode, for the TE, are a function of FC over F, right? So if I make the waveguide, if I choose A such that my cutoff frequency is right around the 10 gigahertz, right? A little bit lower than 10 gigahertz for the TE20 mode, then F will be close to FC. FC will be close to 10 gigahertz, right? And that's going to make this attenuation constant blow up, right? So you're going to get a lot of attenuation if you're too close to the cutoff frequency. And we're operating at 10 gigahertz. We have the choice of A such that we can tune what the cutoff frequency is of the TE20 mode, right? So my suggestion is to pick A such that you are just at the border of when the next mode, I think TE01, is going to appear, right? Probably give yourself a little margin, 5% or so, or whatever, right? So what you want to do is choose A such that the cutoff frequency of the TE20 mode is as far away from 10 gigahertz as you can without allowing the next higher order mode to appear. Higher than TE20, right? That'll make it less lossy. Give you more bandwidth too. All right?
Can I ask a question?
Yeah.
So we can't ever have like TE30 propagate before TE11, right? Because if we made our B dimension relatively small, then you couldn't ever propagate like TE01, for instance, but you could still propagate TE30 if you made A large enough that it could sustain like TE30. Do you see what I mean? Like I'm used to cylindrical waveguides where I would have thought like they have to propagate in the same order. You can't propagate like LP, 01. You can't propagate like LP11 modes without propagating LP01 or whatever.
Yeah, that's right. So if you fix the geometry of A over B equal to 2.25, then it should be well defined. There should be a well-defined mode order, right?
But what's preventing us from making B so small that you can't propagate LP11? But you could still propagate LP30 based on those equations.
Yeah, that I guess that's up to you, right? I guess that is possible. You can make it very thin so that you get the next M mode before the first N one appears, right?
Yeah.
Yeah, so that can happen. As long as M pi over A squared plus N pi over B squared doesn't exceed beta squared, beta not squared, or beta D squared in this case, right? Then you'll be okay.
Okay.
So I would just fix the geometry so that A over B is 2.25. Then everybody's solving the same problem. It's a design problem, right? There's only a few specifications that we need to design. So it is true that you could have done the problem already, assuming a different ratio. That's okay, as long as you meet the objectives of the problem. But if you haven't started it, by the way, the homework's extended to be due next Monday. I don't know if you saw the announcement yet. So not this Wednesday, but next Monday. If you haven't started it, I suggest using that ratio A over B equal to 2.25, and then picking the cutoff the A such that the cutoff frequency of the TE20 is as far away from 10 gigahertz as you can, while simultaneously not allowing the next mode to propagate, right? Because you're going to make A bigger.
So we are doing 10 gigahertz, not 6 gigahertz.
10 gigahertz, yeah.
Is last class you said.
Yeah, I sent out an announcement saying don't worry about that. Because if you had fixed geometry and then you needed to find the frequency, then it's probably around 6. But since we have different variable geometry, then 10 gigahertz is fine.
So we compute the attenuation constant for TE20 or?
So you're going to derive what we did in the notes in your handout or in your the thing that you turn in, TE1 or the TE10 alpha conductivity attenuation constant. But then also state these general ones. I don't want you to have to derive the general ones. That's the point. It's probably a lot of work, right? If they skipped it in the book, then it's a lot of work. Because Bolanis is very thorough. He doesn't mind doing all the derivations. It's a book of derivations, right? But if he skipped it, then there's probably a lot of work. So do the TE10 and then state these general ones and use these in order to calculate the length of the waveguide to sustain only a 0.2 dB loss. And furthermore, since we're going to excite ideally or theoretically only the TE20 mode in the last part of the problem, calculate the length for a loss of 0.2 dB, assuming only the TE20 mode is there. But in reality, that's not the case, right? You'll also have TE10, but it'll be weakly excited because TE20 and TE10 if you put the pin right in the middle, then you're in the null of the TE. No, you can't put it there, right? So, okay, so I'm kind of giving it away. So they'll both be excited, but assume for the sake of a academic problem that the TE20 mode you don't have to consider, because truthfully what you would have is TE10 and TE20, right? And they're both propagating and they both have their own attenuation constant. So you'd have to add up the loss due to both those modes by superposition. But then the problem is you don't know which mode TE10, how much power that one's carrying and how much power TE20 is carrying until you solve the coupling problem in order to add those up to 0.2 dB, right? So you have to come up with 0.2 dB loss, a length to give you 0.2 dB loss, but then how much power should I assume that TE10 is carrying out of that 2 dB, and how much is TE10, 20 and 10? So just assume TE20 for the length calculation. I sent an email for everybody, so you should see it. Yeah. Oh, go ahead, either first.
Is it okay if we don't have the attenuation constant in that exact form? Like I kept mine in terms of beta Z in terms of instead of the cutoff frequency. Like, do you need it to be that exact form, or is that okay?
So yeah, I mean, these derivations, there are lots of pages, right? When you turn them in, and the grader, which we have a grader, what I'll double check their stuff, but to make it easy for the grader is what I'm saying, right? So why don't you go to a form that would be from the notes, but if not, if you do it in terms of beta, it's correct, right? But make it easy for the grader to get your credit, right? So they don't miss something. That's all I'm saying. But if you've already done it, it's fine. If it's correct, right? You'll get the credit guaranteed. Okay, good. Yes.
So when you excite a waveguide, there's a certain amount of power that you're putting into the waveguide, and for each mode that you add on that is propagating, you are always going to lose a certain amount more. So I guess if you have one mode propagating, like the dominant mode, there's a certain amount of power that is lost. But then if you excite it in a way that has multiple modes propagating the same amount of power input, you will lose more power. Is that correct? Or you will attenuate more power.
That is a super good question.
Because of the superposition, the way I'm imagining it is that if each mode propagates independently, then each loses power independently, and there would have to be more for each mode.
Yeah,
right?
I would agree with that, because the magnetic field on the sidewalls, where you calculate the current and then to calculate the loss, is different for each mode. So the amount of power that's lost for each given mode depends on the field configuration and their own attenuation constant, therefore. So I would assume if you take your power, it depends on your couple, right? We didn't solve the coupling problem in this homework problem. That's the problem. But depending on how you couple to each of those modes and distribute that power that you're putting into the waveguide amongst the modes, and how much power each of them get, then you can add up the loss independently for each of those modes over a certain distance to find the L of such that the total power dissipated is 0.2 dB. But we don't know how much power is in each mode because we're not considering the coupling problem in this homework, right?
Don't excite the higher order modes.
So that's typically what's done, right? You have to have at least one mode, the dominant mode, if it's to carry power from the input to the output port. That one mode, you can operate it such that it's only a single mode, right? That's what you probably want to do.
We can have the geometry that sustains higher modes, but we just don't excite those higher modes.
If the modes are supported by the waveguide, they'll most likely be there, right?
Okay.
You can try coupling stronger to one mode, but unless you're in an exact null when you feed the waveguide of a particular mode, maybe that one won't get excited. But most of the times there are some electric field overlapping where, your filament, for example, they put the center conductor of a coax, you put it up into the waveguide, that has some thickness, right? It's not an infinitely thin line. So you'll never be able to put that directly in the null of TE20, for example. So you'll always get, but they'll be weakly excited, right? And it's dependent on the functional inner product between J and FM conjugate, right, of that mode. And also what frequency you're operating at with respect to the cutoff, which is kind of like this, right? So if you're too close to the cutoff, then you get a lot of loss. But if you're close to the cutoff, then you excite it strongly. So yeah. We should have probably talked about the coupling problem. Maybe we can do that later in the course when we have some extra time. All right? We kind of alluded to it, but didn't go into it in depth. Okay, that's all I wanted to say about that. All right. So let's get back to our lectures here. I think we were somewhere around here before, right? Let's see. All right. So let me just walk through really quickly what we did. So we started looking at cylindrical waveguide geometries, and we derived the modes for what the modes supported by a cylindrical waveguide, right? And these modes were found by using, again, a vector potential F or an A, depending on whether we want TE to Z or TM to Z modes, respectively, and applying the boundary conditions in the cylindrical geometry now. And by doing that, we're able to derive mode expressions in terms of Bessel functions, sinusoids, and azimuth and exponentials in the traveling wave direction, in the Z direction, right? So we did that for TE and the TM modes. We found that the mode ordering depends on the ordering of the zeros of the Bessel function. This shouldn't be surprising, right? Remember when we did rectangular waveguides, we had to satisfy the boundary condition at, say, A equal to B, or sorry, not A to B, X equal to A, right? And then we said that the sine function, sine of beta X times X has to equal to 0. And that meant there's an infinite number of zeros of the sine function, right? That meant that m pi is equal to beta X times X, or A, rather. We're evaluating this at A. I should write this down on top. So we said that sine of beta X times A had to equal to 0. This led to beta X A equal to m pi, and then we got beta X equal to m pi by A, right? Okay, but because there's infinite number of zeros of the sine function, then we get this infinite number of modes in the M index, and then infinite number of zeros of cosine or sine in the vertical direction. So we get an infinite number of modes in the N index for beta Y. The same thing's happening here. The Bessel function is like a sinusoid, right? And it's in the radial direction. The boundary condition's in the radial direction. There's only one now. It's in rho equal to A. And there are infinite number of zeros of the Bessel function, just like a sinusoid. So there are infinite number of modes. So instead of sine beta XA equal to 0, we have Jm prime beta rho A equal to 0. And there are infinite number of zeros of that function. So they're kind of derived similarly. And we found for the Tm modes, we had Jm equal to 0, right? Not Jm prime, but still the same concept. We had some mode plots, rectangular or cylindrical waveguide modes that this is the dominant mode here. So we have an electric field here. I think this is a TE mode. So that means the electric field's completely in plane. And we said in order to satisfy the boundary condition on the circular pipe that the tangential components always have to go to 0. And we ended up with mode distributions that look like this, right? Everywhere it has to be normal. Okay, good. And then we ended up here, right? So here are a bunch of mode plots. So now that we're here, let me start the presentation. So we ended up with a bunch of mode plots like this, right? Here's the one we were just talking about, TE11. And these are all the solutions to the wave equation. We solved that last semester. We solved the wave equation in cylindrical coordinates, and we ended up with wave functions, right? The wave functions were Bessel-Hankels, and we ended up with azimuthal cosine sine and exponentials or standing waves in the z direction, right? Good. So we solved those wave functions, and now all these plots here, all they are taking those wave functions and applying a cylindrical boundary condition to them. All these pictures are from that. Why do we have a bunch of them? Because the Bessel functions have an infinite number of zeros, right? Just like the sinusoids did. So these are all the mode plots. This is nothing but the wave equation in cylindrical coordinates. You saw that last semester. We apply the cylindrical boundary condition to it. And now we have all these solutions to Maxwell's equations and the boundary conditions. And that means these are unique solutions. Yeah? Okay, cool.
We don't have TE10.
TE10. Let's find out why TE10 is probably a 0 solution, right? Let's see. TE10, this is TM, yeah? TE10 0. So we're saying, what is TE10? So E rho is there, right? No, wait a minute. Yeah, that's okay, right? This is MN. That is a good question. Why is there no TE10? Let's go back to this thing. So okay, so okay, this is it right here. N only goes from 1, 2 to 3, right? So what does that mean? That means that the second index in this case is not 0 because there is no, that would mean that there are no TE0N modes. Let me just double check that because the indices of the zeros start from 1, right? Let's go back here. Are there no plots that have a 0 as the second digit? And I think that's true, right? That mode is due to the way the nomenclature we've used to identify the modes. The second index can never be 0 because we number the zeros of the Bessel or the derivative of the Bessel as first 0 is the first one, then second, then third, yeah? So it's just the way we name the modes. Okay, good. All right, so to couple to these modes, we have different ways, right? Same as before. We now have probes here. The first one is the TE11 mode here. To couple to the TE11 mode, we want to place the probes in a place where the electric field is it's probably curving around this. So the way I understand this is we have a probe going this way. Maybe this thing has some cylindrical field associated with it. So if you put it here and here, then maybe you can couple to that because the fields are curving there, right? In this case, the TM01 mode has a magnetic field which is circulating, which is similar to a coax cable, right? Okay, here we have, these ones are easier to understand. So here we have an excitation of TE11 mode from the TE10 mode of a rectangular waveguide. So here's the TE10 mode of a rectangular waveguide. It looks like this. The electric field is completely vertical, right? So we have vertical electric fields here, and then they go to 0 at the ends because they're tangential to PEC walls. This mode then starts to gradually, or sorry, the geometry gradually turns into a cylinder from a rectangle. So it's like a smooth connection between, or a smooth, what do they call that? Lofting from a rectangular opening to a circular opening. What that's going to do is, within the waveguide, it's going to slowly and gradually take this electric field, which goes like this, and eventually it's going to bend it a little. So it looks like that, right? As the waveguide wall is changing shape, it's going to start to curve the electric field until it satisfies until it satisfies the right boundary condition. And then here we have TM01 mode from the TE101, which is this mode here, right? So this is probably should have been there, but yeah. So remember the magnetic field, if you look at it in this plane, form these closed loops. So they would go like this in the TE10 mode. And these magnetic field lines are kind of doing the same thing if you look at them from here. So they kind of couple, right? You want to do sort of overlap integrals or field mode matching. Yeah? All right. These are just some pictorial ways of how you can start thinking of how to excite these things. All right? Okay, let's do the attenuation constant for cylindrical waveguides. All right, so we use the same definition. What is the definition of an attenuation constant? It says if I know the power at some reference point, call it z equal to 0, and it's p naught, then after a distance of L, let's say z equal to L, the power is exponentially decreasing as e to the minus alpha z, but this is, or sorry, the power field is decreasing as e to the minus alpha z, power e to the minus 2 alpha z, right? So what we're saying here is that the power P naught at some reference point z equal to 0, this PNM, this is the power in the mnth mode at any arbitrary point z. Well, that's equal to the power in the mnth mode at z equal to 0 times e to the minus 2 alpha cz. Because alpha c itself is a field decay, right? It's e to the minus alpha z. And if you want power, you have to square that. So then you get minus 2 alpha z. So P naught e to the minus 2 alpha c z. Very good. Now, if the power is decreasing as a function of distance, z, within the waveguide, then if I multiply rise over run, or sorry, run multiplied by, so this slope here, the derivative of the negative derivative, dpm divided by dz, is the rate of change of the power with respect to z. It's decreasing, right? Because there's loss. So if I multiply z, which is my run, by negative dpmn divided by dz, which is my slope, which is equal to rise over run, then I get, okay, rise, but it's a negative rise, right? Basically, if I multiply the slope by a distance, then I get the amount of power that's dissipated over that distance z. Okay, but we want to evaluate this at z equal to L, some distance L, right? So negative zd by dz, and then we plug in what pmn is here, which is this. We differentiate that with respect to z, but evaluate it then at z equal to L. And doing the derivative of this with respect to z, we get a alpha c that comes downstairs. And then that's equal to 2 alpha c L pmn when we evaluate it at z equal to L. So now we can rearrange this equation to give us alpha c is equal to pc by L divided by 2 pmn. Same exact formula we had for the rectangular waveguide, right? It's by definition of what these attenuation constants mean. All right? So now to calculate the attenuation constant due to conductivity, we need to calculate what pc is, power dissipated into the conductive walls, and the mode carried by the mnth mode. The power carried by the mnth mode, yeah? Cool. So let's do that. Let's derive it for TE01 mode first. The field components for the TE01 mode are here, right? These come directly from our solutions that we derived last lecture, and they're specialized to the TE01 mode. So what do we see? The 01 mode has only a phi component, yeah? That phi component has no angular dependence. So these are perfect rings in azimuth, and they're completely in the cross section. There's no z component. Remember we talked about that at the end of the last lecture. It's here. Purely azimuthal rings, the electric field. Okay. Magnetic field has a rho and a z component because they form closed loops in the z direction, right? And there's also no azimuthal variation in this mode. Why is there no azimuthal variation? Because the index m is 0. And m is the Bessel function order and the order of the azimuthal variation. Jm beta rho times cosine m phi and sine m phi, right? Okay, good. So these are all J0s as well. Good. All right, and beta rho we found is chi 01 prime over A. We get from our table of zeros of the derivative of the Bessel function because it's TE mode. And from here we can find the power to the cross-section of the waveguide. PE01, 1/2 integration of real part E cross H conjugate dotted with ds, where this cross-section of the waveguide is the xy plane, and therefore ds is z hat ds, right? Z hat ds here. All right. And we have only a phi component of E, and we have a rho and a z component of H. Don't forget to conjugate. All right. Now let's do let's explicitly define A naught, 0 to 2 pi and phi, and 0 to A and rho. If we do this cross product, what do we get? After we do the dot with z, right? So we have rho, phi, and z. So rho crossed with phi gives you z. So what do we have here? Okay, let's do this. We have z here. Then we can say we have, you know what? Let me draw it like this. Z. Then we have rho hat. I think the best way for me to draw it is like this. So start from x, y, z. From here, if we choose this point here, then we have rho hat like that. We have phi hat like that. And we have z hat like that. Yeah? Okay, so we need to do phi crossed with rho. Phi crossed with rho gives you negative z. Yeah? All right. Phi crossed with rho gives us negative z. What happened to the minus sign? Did I draw something wrong here? Let me see. Looks good to me, right? Rho crossed phi gives you z. Phi crossed with rho gives you negative z. Okay. And then phi crossed with z is going to give us something that doesn't dot product with z, right? Gives you 0. I feel like there's a missing negative sign here. The conjugate. No, but we still have conjugate explicitly defined here. What's going on here? 1/2 real part E cross H conjugate. Okay. Now, oh, you know what? Maybe the minus sign is from the definition of E phi and H rho. So what is E phi? E phi is positive, right? And H rho is negative. So that negative cancels that negative. All right. Good. All right. So then we have this, yeah? All right. So if you plug in the definitions for these modes, but still, I don't know why I've already would have taken it into account the negative sign here instead of when I substituted for these. It must work out, or else I made a mistake typing them up. So, all right, A01 squared, if you plug in the actual modes, here it is, right? But we have to integrate this Bessel function, the derivative of the Bessel function. We have to integrate that. So how do we do that? Well, the derivative of the Bessel function, like this, can be written, this is a formula from the back of your book, djpcx divided by dcx is equal to minus jp by 1. So you can either add in order or you can subtract in order. There are two different ways to do this derivative. But p over cx jp plus negative jp plus 1, right? So we can take this j0 prime that we have in the integrand in the previous line, and we can write it as the derivative of j0. And the derivative of j0 will come out to just j1. All right? The reason is p is equal to 0, right? So this whole term goes to 0. All right, good. So we can now integrate, instead of integrating the derivative of j0, we just integrate j1. So let's put j1 back in there like that, and let's do the integration. So I've repeated it here on this slide, and we're going to, okay, what are we doing here? The derivative of the Bessel function, we're talking about the derivative. No, this is not the derivative. Error here. The integral. The integral of the Bessel function, the integral of a Bessel function here, x jp to jp squared cx dx can be found using this formula, right? So you guys probably are definitely, or maybe not definitely, I don't want to say that, but you're probably not used to integrating Bessel functions. So these you just have to, whenever you come up to a derivation, you have an integral of a Bessel function, go to the Gradstein and Resnick book, or wherever you like to find your identities, or you can integrate it, right? But this is a special function, so whenever you see an integral of j1 like that, either you go to a table or you substitute the series expansion for it and you do the integration that way, or use some properties of j1 and try to rewrite it in terms of more familiar functions. So you can probably do that, but these integrations of the Bessel functions are most likely somebody did that and tabulated it in a book. Gradstein and Resnick is a great place to look. Okay, so you can integrate the Bessel function. Now maybe this is correct, right? What am I saying here? Maybe, yeah, okay. Maybe this is the integral of the Bessel function. All right. Good. So, all right. So then we can integrate the Bessel function like this, right? So we use this formula here to integrate this Bessel function. And maybe what I mean here is that you can use the derivative of a Bessel function to find its antiderivative and make this kind of relationship. That might be where this comes from. But anyway, you get this in the end, right? Okay. Well, the first 0, now we need to plug in what this is evaluated at chi01, right? So J2 is minus J naught. Oh, I see. So this expression, this equality at the end here, comes from these facts, right? Because you have all 3 of these terms. So you have J2, which you can write back to minus J0. And then you have J1 squared, which you can relate to, or you can calculate it directly, right? 3.83. You plug in chi01 prime and you get 0. So the only thing left is this J0. All right? Good. So now we can write the power in the TE01 mode as the following. All right? So yeah, you have, if you want to do E cross H conjugate, then, and you're in cylindrical coordinates, you're going to have to integrate Bessel functions. That's all that is, right? So the power dissipated on the walls of the waveguide we need next. So PC is the definition of RS over 2, integration over the walls, the surface of the walls, and JS dotted with JS conjugate, evaluated at rho equal to A, right? We want to evaluate the current density at, it only exists at rho equal to A. All right, so you get magnitude of J squared rho equal to A d phi dz. All right, so JS at rho equal to A is N cross H conjugate, or N cross H plus, right? So we want the forward traveling one. And that's equal to rho crossed with Z gives us the phi, right? No, rho, yeah, gives us the phi component of the Z. And then that's equal to, if you plug in what HZ is, you get the following for the surface current, right? Okay, good. So now the power that's dissipated through conductivity can be written in the following way. We take this JS, we square it, and we integrate it, and we end up with the following. So here we're not integrating with respect to rho. So we have a Bessel function here, but we're not going to integrate with respect to rho. We're evaluating it at rho equal to A and integrating with respect to phi and Z. So we end up with this. Z only for length from 0 to L. Okay, so if you divide both sides by L, then you get this expression. All right, now we can make the attenuation constant, because what did we need? We needed PC over L and PMN. So we've done that now. Good. So alpha 01 TE to Z. All right. So this is kind of cool, right? RS over A into eta. It's a function of FC over F squared again. And this ratio, or square root of 1 minus FC over F squared. Interesting, yeah? All right, so what do you notice about this? Let's see if we can see it. So without derivation, the attenuation constants due to the conductivity in circular waveguide for N modes instead of 0, 1, same as we did for rectangular, are stated here, right? Without derivation. So what is really cool about these things, first off? One thing you might notice for these TE modes is that the power, or the attenuation constant, decreases with frequency, which normally doesn't happen, right? It's normally the other way around. Only for TE0N modes. All right? So let's look at that really quick. That's going to be one conclusion that we derive. I'm showing two plots here. They're for cylindrical waveguides with free space inside and copper walls. The two plots are associated with A equal to 1.5 and A equal to 3 centimeter. All right? We're plotting alpha in the units of nepers times 10 to the third per meter as a function of frequency, which is normalized with respect to FC11 of the TE mode. All right? Okay. So these are for, we're showing a few curves here. TE01, then 02, TE11, TE21, TM01, TM11. All right? And we're assuming the conductivity of copper. So what do we see here? For any mode that has 0n, so any mode that has m equal to 0, so this mode and this mode, the TE modes, right? That have m equal to 0, so the solid line and the dashed line, which is this one and this one, right? These two modes, as the frequency increases, the attenuation decreases, which is normally not the case, right? So these are kind of special modes. They've been studied a lot. A lot of people do a lot of work in how to utilize this physical fact in order to derive or to design communication links that use cylindrical waveguides, right? The higher the frequency, the less the loss. That's really cool. Okay, why do you think that is? Remember TE0N modes. Why do you think that is? Maybe you can remember.
It's moving so fast that the atom doesn't move at all.
That's dielectric, right? Whenever we have a dielectric and we're polarizing an atom back and forth, if we excite it with a high enough frequency, then the inertia of the electron cloud can't keep up with the incident signal, right? looks transparent at high frequencies.
What does this mean for conductive material though?
So there's no restoring force here, right? So these are Drude electrons, they're free to move. So they're going, okay, so there's probably dispersion, right? Of course, the Drude model is dispersion. But as far as having the electron's not able to keep up, that probably is the case if you assume that there's some
Like,
collisions and things.
it's kind of sloshing around.
Yeah, but I think, don't think about it that way, all right? That's an observation, that's a good thing to think of, but why are the TE0N modes, the higher the frequency goes, the less loss? Yes?
Does it have anything to do with when we saw the TE01 mode, the electric field lines do not contact the outer walls?
Yeah, exactly. Very good. Remember, these mode profiles here for the TE0 modes, 0N, remember we talked about these last time. They have azimuthal variation, right? So if M is equal to 0 for TEMN, then it's always J0, and there's never any azimuthal variation because it's cosine M phi, sine M phi. So if M is equal to 0, then you always get phi independent or azimuthal independence or phi independence and only a phi components, right? Because if you look back at, so here, look, here's TE02. All right. And remember the loss, you calculate the loss by integrating the magnetic field. Of course, there is a magnetic field here, so it might be a little more subtle than that, but that's a good observation, right? The 0N modes, they don't really have tangential E, yeah? Okay, good. So that's an observation, right, from these things. All right, so that does it for our circular waveguides, yeah? So what are we going to study next? We're going to do circular cavities, just like we did with the rectangular geometries. Then we're going to look at circular dielectric rods that are also waveguides, right? So instead of a dielectric slab, we're going to look at dielectric rods with circular cross-section. Then we're going to do the same thing we did with the dielectric covered ground plane, where we're going to do dielectric coated metallic rods. If you don't remember, last semester we studied these same geometries, but we were looking at scattering problems, not waveguiding problems, right? We studied the scattering from a cylinder, an infinite cylinder, by a plane wave, by doing mode matching. We studied scattering from a dielectric covered cylindrical rod, metallic rod. Remember we did that problem as well? We did do scattering off of oblique incidence cylindrical metallic rods, right? And we also scattered off of all kinds of rectangular geometries, right? But here we're going to treat the same problems as cylindrical dielectric waveguides. We'll do that next, right? We're going to do cavities first, so I'm kind of getting ahead of myself. All right, so circular cavity. For the circular cavity, we do the same thing. We use the same vector potentials, F and A, but in this case, we now have an additional boundary condition that's applied at Z equal to H and Z equal to 0, right? So we close off the waveguide and make it a height H. So for the circular cavity, we can reuse the vector potentials, only now we do the same thing we did in the rectangular case. We modify the z-directed wave functions to represent standing waves rather than traveling waves. So these standing waves are cosine and sine, right? We still have the same dispersion relation here, and we found before that the beta rho is not going to change because we're only changing the z-directed wave numbers by putting these short circuits or these PEC caps on the ends, right? So now our boundary condition in E rho and E phi are the same, right? So E rho, why is this? Oh, because we're at the end of the cavity now. So there's a new boundary condition, E rho, right? E rho normally doesn't have tangential components to PEC, but in the case of a cavity, E rho points parallel or tangential to the end caps, yeah? All right, good. So this is a new boundary condition here, and this is also a new boundary condition at Z equal to 0 and Z equal to H. The tangential components must be 0 at these points. So we have E phi here, E phi at Z equal to 0. We can calculate E phi from FZ, now that has standing wave solutions in the Z direction by using the vector potential definition. We calculate that by differentiating with respect to rho. Jm picks up a rho, or a dash. Jm picks up a dash, or a prime. All right. This all has to be equal to 0 whenever we substitute Z equal to 0. So substituting Z equal to 0 here makes the sine function go to 0, but cosine of 0 doesn't go to 0, so C3 must be 0. And that's the conclusion from the first boundary condition. All right, E phi at z equal to h now also has to be 0 because it's tangential to the PEC on this surface here. And we calculate E phi by differentiating Fz with respect to rho. So J picks up a prime. And we already know that C3 is equal to 0, so we only have the sine function here. There should probably be a D3 here because we haven't lumped the constants yet. But the only way this could be 0 if sine of beta zh is equal to 0, and there's infinite number of zeros for the sine function. So that means beta z times h has to equal to p pi. Now we include an index p. Or beta z is equal to p pi over h, where p equals to 1, 2, 3, etc. Yeah? Okay. Resonant frequencies of the modes we can now find using our separation relation. Remember, we already know what beta rho is from our solution of cylindrical waveguides. Now we know what beta z is from our solution of the cylindrical cavity. And we say that this is equal to some beta resonant squared, which is omega resonant squared mu epsilon. We can rearrange this equation to get the same exact formula for the cutoff frequencies, right? Or not the same exact formula, it's a new formula because of this, right? Now we have a discrete index in the z direction. All right. So now we have mn and p, and they increase like that. Okay, so, and remember, just as a reminder, this is the table that we had from before for the zeros of xm prime here. All right. So let's calculate what the dominant mode here, TE mode, which is TE 111. All right, MNP equal to 111. Why is that the dominant mode, right? Because here are the tables of the zeros of the derivative of the Bessel function for TE modes, chi mn prime, right? And we know that this is the lowest number in the table, which is associated with m equal to 1 and n equal to 1. And p has to start from 1. So 1, 1, 1 is the first mode, the dominant mode. If you go into CST and you model, a cavity, a cylindrical puck or a disk of air, and you make the background material PEC, and you run the eigenmode solver, then this is what you get, right? For these dimensions here that I chose. All right. The first three modes are TM modes, so ignore those. But the first TE mode is this calculation here, and that's what we calculated, right? So the calculation works, of course. All right. Let's look at TM to Z circular cavity modes. Yes, TM to Z. So circular cavity modes for TM to Z. For the circular cavity, we can reuse the vector potentials, only now modify the Z-directed wave function to represent standing waves, but now we choose A, Z, right? Because we want TM modes, TM to Z modes. All right, these are standing waves in Z. We have the same separation relation, except beta rho is now related to chi mn and not chi mn prime, because these are TM modes over A. And we apply the boundary conditions, E rho and E phi, Z equal to 0, Z equal to H. We evaluate E phi again, but now this is the formula for E phi. It's minus J BMN. I didn't include the formula, but we do different derivatives when we're doing TM, right? It's not, because it's a different derivative, right? Okay. So E phi now, we have a JM prime, and we have the following. I'm surprised that this is JM prime. I need to check back at that because all three of these wave functions are then differentiated, and I don't think that's the case. So TM modes, let me double check with the cylindrical. Sorry, give me 1 second. So we're talking about TM modes now, yeah? These should not be primed, is what I think. Here's the formula, E phi for TM, right? So we should be differentiating with respect to phi and Z. That means we should not have a prime on, so there's a typo here. Let me just make sure I fix that for you. Here. There should not be a prime here. This is copy and paste error. So no prime, yeah? There and here. All right, so we differentiated phi and z, right? And then we plugged in z equal to 0, and from there we conclude that d3 has to be 0 because d3 has to be 0 in order for this whole thing to go to 0. Now we plug in z equal to h, and what we find here is that beta z h must equal to p pi, which is beta z equal to p pi over h again, right? Okay, good. Okay. So the resonant frequency of the modes we can now find by going back to our dispersion relation and doing the same exact thing. Chi mn now instead of chi mn prime over a whole squared plus p pi over h whole squared equal to beta r squared, which is omega r squared over times mu epsilon. So fr tm into z modes of the MNP, the resonant frequency of the MNP index mode of the tm to z mode set is equal to 1 over 2 pi squared of mu epsilon times this. The only difference between the previous one is there was a prime here, and the index here started from 1 instead of the different starting points of the indices. All right, so let's calculate for the 010 mode and for the 110 mode for the TM. What do we get? Why do we choose these? 010 is this one. The first lowest number in the zeros of the actual Bessel function is 1. And P must start at 0, right? So we have 010, and then the next one is 110, right? If we do the calculation, we get 10 and 16. If we go back to the eigenmode solution of the cylindrical waveguide cavity, then we find these first two modes are the modes of interest. This third one is just a degenerate mode, meaning it's the same mode, but it's rotated in polarization. All right, so it agrees. These are two TM modes, TM1, 010, 110, and then this one was our TE 111 mode, right? Yeah.
When you have two modes at this set that are at the same frequency, same cutoff frequency, are they both called degenerate modes? Or-
Yes. Yeah, they're both degenerate modes. Yeah, they're both degenerate modes at the same. These cylindrical waveguides have a lot of that because there's it's ambiguity in the direction of a mode, right? Clear-cut direction. Yeah.
I'm pretty sure you explained this before, but why exactly is P starting from 0 here and it was starting from 1 for DE?
So what happens is you throw out a set of modes depending on whether they're trivial solutions, right? So if we were to go to the fields derived from this vector potential with these boundary conditions, then what you'd probably find is if I plug in P equal to 1, all the electric field goes to 0. No, sorry, not P equal to 1. In the previous one, where we couldn't have 0,
Yes.
right? If you plug in P equal to 0 in the TE modes, then there's no electric field at all. So it's a trivial solution. So we throw that one out. Yeah? You could start from 0 on both of them because sine of n pi has 0 as a solution, right? Sine of beta zh equal to 0 has p pi with p equal to 0 as a solution. Okay, so but if you do that, the electric field is 0, all of it. So the mode is a trivial solution. So they exclude that, yeah? All right, good. So let's look at what we have here. Here I've plotted the CST simulation for the electric field of mode 1 and the magnetic field of mode 1. And we see the characteristics of resonators, right? We have 90-degree out of phase oscillation. When the electric field peaks, the magnetic field goes to 0. When the magnetic field peaks there, the electric field goes to 0. And it's like exchanging energy between the electric and magnetic fields, similar to a tank circuit, which is also a resonator. These are resonators, right? Where you have an inductor in parallel with capacitor, and you're exchanging energy between the electric field and the magnetic field stored in the inductor or in the capacitor, yeah? Same thing, yeah? So we should see the field configurations or the definitions of the electric field and magnetic field should have a J difference in terms of the phase. So this is a real number, chi01, A is a real number, beta or B010 is a constant, M or mu is a real number, and J is a real number, right? So this is a real number. This one has all real numbers as well, but we have a J out front. So they're 90 degrees out of phase, right? A J is e to the J pi over 2. All right, good. And that means that these will oscillate out of phase. Okay. Let's see what all we got left here. So let's look at the mode order now. How do the modes appear? So for cylindrical cavities, it's a little bit different than rectangular cavities in the sense that the dominant mode depends on the geometry's aspect ratio. So for example, when h divided by a, the height divided by the radius, is less than this magic number 2.03, then the dominant mode is TM010. And we just saw that, right? The dominant mode was TM010 in the CST simulations. Whereas when h over a is greater than 2.03, the other side of 2.03, the dominant mode is TE111. All right, so if we look at this table, what do we have? We have ratios to TM010 until h over a becomes greater than 2.03. Then it becomes ratioed with respect to TE111, right? So look at here. This is 2.03 in this table. We're calculating what's shown in this table is R, the ratio of the MNP mode to whatever mode is dominant. So that's the resonant frequency of the MNP mode with respect to the resonant frequency of whatever dominant mode is. For this part of the table, we're showing H over A, which is this quantity, 0, 0.5, 1, and then 2.03, right? That means that the dominant mode when H is less than 2.03 is TM010, and you'll see that here. It's the ratio to TM010 everywhere, yeah? Once you increase beyond H over A equal to 2.03, so it's this half of the table, the ratios are now taken with respect to TE111. All right. And here are the ratios. So if I know the resonant frequency of the TM010 mode for the cavity, why am I listing them like this? I guess I said it like that. But why am I listing them as ratios, right? Because otherwise I'd have to pick a specific geometry with a specific resonant frequency, and then I'd have to list the resonant frequencies with respect to that geometry. But by writing them in terms of an H over A ratio, I can make general conclusions about the ratios between whatever geometry I have, a general geometry, and the resonant frequency of the dominant mode for that geometry. So all I have to do is calculate the resonant frequency for the dominant mode, and this ratio then gives me the resonant frequency of the MNP mode. All right? Good. All right, very nice. And in here you can see the order of the modes, right? By listing of the resonant frequency. So here, obviously the TM010 mode ratio to itself gives you a ratio of 1. And this is the dominant mode. When H over A, okay, H over A of 0, that's kind of, I don't know why they would put that in this table. I guess what they're showing here is the height is kind of independent until you get to higher order modes here. So these first few modes have the exact same ratio as a 0.5. But what does it mean for H over A to be 0? It must be a limiting case, right? I don't even know what that means. It's just a disk then. All right, anyhow, let's look at this row then, 0.5. So the next mode is the TM110, because these are listed in increasing value, right? So goes TM010, 110, 210, 020, 310, TE111, TM011, right? And then here, once you're greater than 2.03, then it's TE111 first, then TM010, then TM011 instead of 210, TE112 instead of 020, and so forth, right? All right. Good. Okay. Let's derive the quality factor for these resonators. So we'll derive the quality factor for the dominant TM010 mode, which is the dominant mode when H over A is greater than 2.03. And for the TM010 mode, we derived this potential, right? It reduces to this, A of Z. So 0, 1, 0. 0 is M, so TM010, which is M, N, P, right? So tell me right off the bat, if we have 0 for M, what do we know about the field profile? Before you look, All right, Stan, over here. What do you know? No azimuthal variation because M is the azimuthal index, right? Well, what else? What do we know about the row variation as well? Remember, M is the order of the Bessel function and the order of the azimuthal variation, right? So they're linked by nature of how we solved the wave equation in cylindrical coordinates. So if M is equal to 0, there's no azimuthal variation, and we know that it's J0 only, right? J0. Okay, that's good. All right, what about N? Well, let's look at P. What does P mean if it's 0? P is the order of the Z-dependent variation, right? So what are we saying here? No Z-dependence. It's constant in Z. Constant in rho. No azimuthal variation, right? All right, and then N is just the number, the ordering of the index of the zeros of the Bessel function. We're taking the first one. And N has to be at least 1. N can't be 0. So this means that these fields have, they have radial dependence based on J0, no azimuthal and no Z dependence. That's exactly this, right? This vector field here has EZ only, and it's not a function of Z. And it's not a function of phi. And it has J0 type of row dependence, right? J0 is like a decaying sinusoid looking thing, right? All right. And that's why we have AZ here as J0 only. Very nice. So, and then beta rho is like that, right? For the 0. For 0, 1, chi 0, 1. So E rho is 0. E phi is 0. EZ, we saw this on the last slide. H rho is equal to 0. We have a phi component only of H, and it also has no azimuthal variation and no Z-directed variation. So it's constant in Z, constant in phi, and it just varies in rho. And then we have no Z. It's exactly this, right? Okay. Let's derive the quality factor for that mode. So we have the field configurations. We need to calculate, by definition of what a quality factor is, it's the energy stored by the power dissipated, yeah? So we need to calculate W and P. W is equal to twice the electric stored energy, right? Because in a resonator, you either have, there's equal energy in the magnetic and the electric field, right? So epsilon over 2, integration, magnitude E squared dV. That's how you calculate what WE is. Actually, WE itself is epsilon divided by 4. And then you integrate the electric field squared dV. Where does this come from? Let me see if you guys remember from last semester. What formula is the step just before you get to this one? Yes. Not pointing vector, right? Pointing vector's power.
Grading the volume, it's divergence.
Okay, divergence maybe can lead to it. Remember, you have the integration, so it's epsilon divided by 4. Epsilon only comes out after, right? So it's the integration over the volume of D dotted with E, right? And I think there's a conjugate in one of these in time harmonics. All right, and then D we know is epsilon E, and that there must be a 1/4 out here. I think a 1/4 comes from peak to R mass, and then there's also, when you combine these derivatives, you get a 1/2 there. All right, so this becomes epsilon over 4 volume of E dotted with E conjugate dV, and then you get that formula, right? What about the other one we used, where we were calculating the power dissipated? What about this one? Remember, power dissipated, what we saw before is the integration. So this comes from the integration of, I believe there's a 1/2, and it's the integration of J dotted with E conjugate, right? D dotted with E, J dotted with E, and B dotted with H. Go back to the lecture where we derived the conservation of power theorems. All right, anyhow, that's where this comes from, right? So we need to take the electric field for the z component and we plug it in here and we integrate over the volume. Have to take its magnitude squared. All right? And if you do that, you get this expression here. We still have to integrate the Bessel function squared. We've done that already. With the integration of rho j naught squared, chi O1 over a rho is equal to d rho, which is equal to a squared over 2 j1 squared of chi 0, 1. Because of that, we can write the stored electric energy as this expression here, yeah? All right. Now, since the cavity is filled with lossless dielectric, all the power that's dissipated is dissipated into the conductivity of the walls of the cavity. So we have the integration over the area of the cavity resonator, Rs over 2, integration of h squared ds, yeah? You guys know where this comes from, yeah? Okay, so we have to integrate over the whole area. We have we have one cylindrical side where we're integrating at rho equal to a from 0 to 2 pi n phi and 0 to h and z. That means we're integrating the side of the cylinder. And then we have two end caps, a top and a bottom end cap. So a 2 times the integration from 0 to 2 pi n azimuth and 0 to a n rho evaluated as equal to 0, right? So that's the whole surface area of the cylinder. All right. So, okay. So you take the H field, H phi from the previous slide, and you plug it in and you get the following two integrals, right? You get this integral and this integral. And the first one you can solve. What am I doing here? So the first one you can solve using the formulas we derived before already previously. All right. Then I've repeated the expression up to this point here. Now we have to integrate this j0 prime. So we rewrite j0 prime as minus j1. We did that before as well. And at rho equal to a, we have so we have j0 prime is equal to minus j1 chi equal to 0 because we plug in rho equal to a here. These a's cancel with the rho. Yeah. All right. So we can plug that in now. And we end up with this integration now of j1 squared instead of j0 prime squared. And when we do the integral, we end up with this expression here from the formula we derived before. And now we have our dissipated power. Now the quality factor we can write like this, omega times energy stored divided by the power dissipated. If you do all of this ratio, you end up with this expression here. Good. All right. So that's the expression there. So it's dependent on A over H and eta, right? Let's do an example. Let's compare the Q values of a circular cavity operating in the TM010 mode of those of a square-based rectangular cavity. We did this calculation in last lecture, right? So the dimensions of each are such that the circular cavity is circumscribed by the square-based rectangular cavity. Namely, a square-based rectangular cavity circumscribes a circular cavity when one of the sides of its base is equal to diameter and their heights are equal. Let me draw a picture. So what we're saying here is that we have a rectangular cavity like this. So, and then it goes like that. Okay, the circumscribed circular cavity has, let's draw it in a different color maybe. How can I do that? Like that. Looks like this, right? It has the same height. So what are we saying here? We're saying this, right? A, which is this cross, which is the x dimension of the rectangular cavity, is equal to C. It's a square-based cavity. And that's also equal to D, which is the diameter of the cylindrical cavity, right? So the diameter is equal to the length of the side of the square-based cavity. All right. And they have the same height. Okay. Circular cavity, we derived this formula. Rectangular cavity, we derived this formula before, right? Okay. If you ratio those two things and by comparing them, then what you'll find is that the cylindrical cavity has 8.26% greater Q. Yeah. The cylindrical Q is higher than the cylindrical cavity Q of the same similar dimensions is higher than you have a higher Q in a cylindrical cavity than you do in a rectangular cavity. And that's because the rectangular cavity has a bunch of sharp corners and things that can easily lead to loss. And the cylindrical cavity is a more of a smooth geometry, right? And then also we remembered that Q is proportional to the volume and inversely proportional to area, right? We'll get to that next. We're gonna do spherical. Yes?
Explain how the corners would negatively impact the Q factor.
So whenever you have sharp corners of anything or like finite sharp edges, you end up with a lot of charge there to satisfy, especially PEC. But even if you have a little bit of conductivity to lead to loss, then you end up with a lot of charge there. And if there's a current, then you have a very strong current there, right? Which means you have a lot of you have more dissipation at these finite edges. We'll study that in method of moments, but for example, if I have a PEC plate like this, PEC for now, and I illuminate it with an electric field that is like that, right? That's traveling in this direction. Then what happens is that the current distribution on this PEC finite width strip looks like this. It's singular on the edges. Why is that? Because this finite edge here requires an infinite number of charge in order to give you zero tangential electric field there. One way we can think of it is like this. So here's a strip, right? PEC. Now, I have a bunch of charges on here, right? How do they distribute themselves? Let's say they're plus charges, like a static picture. They distribute themselves such that the electric field generated by this positive charge, which points that way, is exactly canceled by the electric field of this positive charge pointing that way, yeah? So let me draw them in a different color here. So this one generates an electric field going that way, right? This red one. And then the blue one generates an electric field going that way, this blue charge. They're distributed such that those two electric fields that are tangential to the PEC go to zero by a boundary condition, yeah? All right, but what happens when you get to the edge? So here, there's more, right? Then you get to the edge. So this is fine for the center. When you get to the edge here, this one's generating electric field that way, but then you need another one here to generate electric field that way, but there's not enough conductor left. So they start bunching up all close here, trying to cancel each other's tangential components at the end here. And you get it's a singularity really. You get a lot of charge there, right? And the current, therefore, since the electric field's in and out of the board, all this charge that's needed to satisfy the tangential boundary condition, or the boundary condition of tangential E equals 0 there, is going to be in motion in and out of the board, and it generates a very strong current. Yes?
This is only when the conductor's in the presence of an electric field. Like
Uh,
a charged piece of conductor, would this still happen outside of an electric field?
Yes, right? Because if you have charges at all on a piece of metal, whether that's immersed in an electric field or not, those charges generate their own electric field. So I can take a conductor, place some charge on it, and then turn off all electric fields or walk away with any other fields, and those charges will redistribute themselves on that conductor such that there is no tangential electric field on the PEC, or in other words, the equipotential. But if it's a finite conductor like that, you're going to need neighboring charges to cancel the electric fields. And since there's no conductor left for them to disperse, they're just going to bunch up at the ends. I know it's a qualitative description that I'm giving you, but there's a more quantitative model for that. But that's kind of the idea here. You're running out of conductor and you keep adding more and more charge to cancel the ones that are neighboring it. Yes?
So then that sort of singularity of charge is generating, like, in between them that they're canceling each other out, but around that singularity is a stronger electric field than there is anywhere else. So is that canceled by the total electric charges away from it? Does that make sense?
You will get a strong electric field at sharp points and at sharp edges and corners and all that, right? And that's why this cavity has stronger currents there in the corners. But what's canceling this probably, the only thing that has to be satisfied is tangential E on the PEC, right? It doesn't matter what other charges over here. whatever charges are in this space are going to cause the charges on the PEC strip to always satisfy the boundary condition. They have to give you tangential E equal to 0.
1.02 times 1.117.
Yeah, that comes from the solution. Remember, these are TE, the dominant modes here. So let's go here. That comes from chi 0, 1. Chi 0, 1 multiplied by square root of mu over epsilon. Or no, just chi 0, 1. Plus some other constants, right? There's a divide by 2 here. So what is chi 0, 1? Let's find it for, I think I stated it here. Chi 0, 1 is 2.4049. If you divide that by 2, then you get 1.2025. Yeah?
So how does the change in geometry emerge? Change in the number?
Change this number. This number does not change with geometry. It changes with the mode. Remember, this is for the TM010 mode. This is mode dependent. The geometry appears here in the denominator as A over H.
But you are saying that because of the corners, we are having a difference in the value.
The corners cause there to be a higher current charge density, which is associated with a higher current density, and we're integrating sigma times the magnitude of J squared, right? So that leads to more loss. Stronger the current, it's like a dielectric, right? If I have a dielectric and I have a printed circuit on top of it, if I have like a capacitor or something with a strong field in between the gap, then there's going to be a stronger field in the dielectric region, and the loss in the dielectric is proportional to the electric field there, yeah? Strength of the electric field. Okay. So yeah, that's that. So we're going to look at next semester or next lecture, circular dielectric waveguides, where we have, these are very interesting. They're a little bit different than what you might think of because the modes in here are typically hybrid modes. And we're going to have to understand what a hybrid mode is. It's a mixture of a TE and a TM mode. So it's not very clearly defined as it was for all these other geometries, right? But we're going to study this dielectric waveguide next lecture. Very good. Any questions? All right. Start your homework. I extended it for a few days, but don't rely on that. So do your homework, and it will be due a week from now. And you turn it into Canvas, and it has to be turned in before the start of the class, or you won't be able to turn it in because the submission window closes at 4 o'clock on Monday. All right? Good.
Thank you.
All right. Have a good one. See you guys.
You know he's doing instance? Oh, no, sorry. You're good.
Said Alec?
Yeah.
I finished it one way, but I went the long way, so I'm gonna simplify it.
You want my number so you can know?
Yeah.
You too. See you later.
I was like, man, I'm never gonna meet like anyone
Oh, yeah, you got two of us actually.
in this class in person, yeah.
Is this number, sorry?
Oh, sorry. Yeah, it's Nick, it's first name, or last name, and then numbers. My bad.
William, right?
Mm-hmm. Yeah, I'll text you.
Yeah, man. Hey, you can always ask me questions.
Appreciate
This is my advisor, so it's
Oh, really? He's on my committee, but he's not my advisor. My main advisor is Dr. Brad Davis, but he's over at
Davis.
Hume. Really?
Yeah,
How about that?
You part of the Hume Center?
Mhm.
Oh, damn. Yeah, he wanted to do it.
See you guys.
Yeah.
Yeah, but that was not too bad though. You took on like J, beta, delta Z over 4 pi, I think, something like that, the
Are you
constant.
talking about the constants?
Yeah.
The second number?
He just said make sure to do the dimensional analysis to verify
Yeah, you always said them.
Yeah, I
I'm
know.
straight to the current, this might be a dumb question, the current filament, I thought was like. It was like J is equal to I delta L delta V, something like that.
Yeah, yeah.
Current versus current density.
Did you also type out your answer or did you write? on a
Yeah,
paper?
I typed it out in LaTeX.
Yeah, they give the oddball out here.
Did you, well, yeah, because you said no handwriting, so I was like,
Ah.
it's in the syllabus, yeah, no.
Yeah, I mean, I thought he wrote that ad on that it's B. Like in the
Oh,
first
no,
place.
it straight up says no.
So he's been, I've been his student for like 4 years. Know what the heck it looks like.
Okay, that's
Yeah, I don't. I need to pass on this to myself. Yeah, I would need it.
One over 4. Not really. 1 over 4 is not right. One.
Did you guys also have the same?
You all have the same figures for.
No, the same comment that it shouldn't be from 0 to 360. It should be from 0 to 359, right?
Yeah, I think that.
Yeah, I see.
Well, it might be, it's just like. There was no like. It's off the prerequisite.
There.
Oh, yeah, well, it's not like it was my first time, I've actually got a CC class I went like 6 times over break. But I started like trying to do like jumps and tricks and stuff, and that was, I'm sorry, very good. It's all good, I'm gonna get it off in a couple weeks.
Is that just a spray or like a fracture?
No, it was a fracture, yeah, but I'm left-handed, so.
That's very. Right. What are the courses happening?
Have I taken?
Yeah, like apart from these two. Yeah, no. It made me wanna.
Do your research.
I had an interview.
Okay.
I was like, oh, I
RF.
That got doing.
Counting, 4,000. No, it was tough with, well, actually it was tough by phone. Does Lynn teach you? Well, that actually sounds nice because she does like, does she do like the electromechanics?
To be honest with you, strong is not. That's.
But when I took it with Falk, it was all like, it was all, yeah, he's a good guy, but it was like no physics. It was like all like electromagnetic or all like model, communication models.
So it's serious.